So just because of the researchers asked me and people asked me to explain a little why recording with polytroid is so difficult, because many people try to record with polytroid and very difficult to get signal. So I'm going to explain very briefly the procedure. So I have a mouse, and Paul Chadderton, which is was my co-supervisor at Imperial College London. He had a very nice setup with a how do you call it? It's like machine that compensates for the. It's a mechanical machine. It's like a table, sort of like a amortiguates any tiny movement. So it's like it doesn't move at all. And then inside that, I mean, on top of that, he had like a chamber, which is called anechoic chamber, and that protects from the noise, but also amortiguates even more the movement. So it was completely shielded from noise and movement, the mouse inside. And then inside you have to secure very carefully every tiny part. And then the craniotomy was an entirely different technique. I developed myself. I don't think it makes case. As I said, it's very important to don't hit blood vessels, keep the tissue healthy, and on top, I advised by Paul. I made because he read it on a paper. I made I built with ACSF tiny sheets, as in microscopic thin sheets of agar with ACSF, so to protect the brain and keep it moisturized. And also that the thick layer of agar would stabilize the probe and prevent from having vibrations on the probe. And that, along many other precautions, allowed to record signal, those tiny signals that I think they're gorgeous. So I think I'm very proud. No, they're not simulations. I'm just saying that because many people say they're simulations. No, they are not simulations. They're real signals. And it is possible to record with those electrodes. It isn't impossible. It's just a lot of hard work. So on the right, one of the aims of my project was to classify the neurons based on the morphology. So on the first column, for 4 neurons, I have the original pattern for the sodium peak. And then in the middle, the peak to trough, I mean the full amplitude heat map. And then on the right, the reproduction I achieved with my model, which I call mixture of a Gaussian model, which is actually just 2 Gaussians. It's sort of more or less like nothing fancy and nothing out of the ordinary. 2 Gaussians with a specific center and with a standard deviation on both axes and with a rotation. And that allowed me to represent most of the patterns, spatial patterns that we found on real recordings. And so why is this important? Yes, because ion channels are the origin of signals. So these signals I recorded, that's what the point was, that the signals I recorded were extremely low in amplitude and extremely clean. As in my record, you can see the white noise from the electrical recording system called Theta Array, Theta Data Acquisition System from Neuralinks. And it has a very clean electrical noise, very low. And on top of that, you have a very small signal, which is on the order of, it can go like 10 microvolts and less, and it's already visible. So that's why it's important, because the signal comes from ion channels, and we were aiming to see even the tiniest of branches and dendrites with the tiniest signals. So talking about the model I developed for classifying the neurons. So the objective of the model was to classify the neuron based on the morphology. So the model was chosen in a way that it would first reproduce the spatial pattern that we see on the electrodes as seen here, on the first two columns on each of the 4 neurons displayed on the right. And for example, those, and apart from reproducing the pattern, to choose a model, we needed to have parameters. So a model that has parameters to characterize and sort of cluster the different patterns that you find based on the parameters. So there are models that might reproduce with low error. For example, you could just use 1 big blob instead of 2, and the error would be low. But then you wouldn't be able to separate one neuron from the other, because here you have 2 blobs, 2 peaks, and on the other you have 1. So that's the reason to choose this model. There are many other models, I think, that we could have chosen. We could have developed many other models, I think, and they would do the same. Maybe even the same line source. Maybe. No, not in this case, but other models. So, and on the left I'm just explaining the the mixture of Gaussian model, which is taking, so a Gaussian is e to the minus d square over sigma square. So d in this case is the vectorial sum of x minus xc and x minus I minus I sub z. That's the distance. So I think for what I remember, I sort of like applied on that the sort of like the I don't know how to say it in English. It's like curva de nivel, so where you need the same level, and oriented the filter was oriented on a theta angle. So it's just 2 filters oriented each at an angle and with different deviation along the x and the y axis. And that's the model we used, and all these parameters, the theta and the sigma and the amplitudes were used. I think the relative amplitude was used, or normalized amplitude were used to fit into cluster and classify neurons. So repeating the same image on the left side is showing an example of how we manage to reproduce the spatial pattern even outside the array. So doing that is very complex because it's like a considerable amount of information that you had to extrapolate. It's not visible on the array. So it's a fairly good result to being able to sort of like guess what was on the other side. Probably in many cases we will be far off what the true is, but in many cases of interest, as this on the bottom left, where you have 2 sources, like clearly a distinct type of neuron, and it's very useful. And in other cases where it's like slanted or oriented, and clearly you would aim outside of the array with the model, it would be also the ideal model because you can easily guess what is outside without being wrong. In the sense, for the motivation for this model, which was to classify the type of neuron, maybe not as much as to reproduce with high fidelity the amplitudes, because for that we use the other model, which is the line sources. But for this, which was to classify, it is highly accurate, I think. And we verified this on simulations. So I think, so on the left, those are real recordings. That's the important part. On the left image is real recordings, and on the right side, I'm showing on the A, we're showing the column FK, focus and malo index. No, sorry, the FK index, which is a method to based on an iterative correction of a k-means, where at each step you calculate an alpha weighting index that sort of like considers the previous weighting index from the previous clustering result, and the FK repeats that considering the features, the distance of the features on the cluster, plus the weighting factor to calculate F sub k. So F sub k has the mathematical property that converges to 1. And the method they published was that as you increase the number of clusters, it converges to 1, and any particular behavior that deviates from 1 is potentially a clustering result that is of interest, because it has a in this case, for example, it would be like it's better cluster. So you have the distance from the on each cluster to the other ones is less. So when you have, it deviates from the saturation. When it doesn't matter how many clusters you do, it saturates. And when you have something that it performs better, the correction algorithm mathematically allows you to indicate that by moving away from 1. And that's the old technique that we use, because for a small cluster where we have, like, for some type of neuron, we could have recorded, for example, 2 or 3 on a dataset of 100 of neurons, because there were like just 3 of those. So you need a very specific type of clustering technique, and all techniques that are fairly simple, as in sort of like we arrange them and then we sort them, those are the same, and then we just quantify with some metric how far off we are from minimizing some kind of statistical similarity. Sometimes they do better than other pure k-means or clustering based on non-statistical distribution, as in assuming that they are Gaussianly distributed around a mean, or uniformly distributed around a specific feature, some features. So just to remind you of the purpose of this presentation was to show